Hi there, and welcome to another installment of knowledge regarding classification in the linear sense. In other words, welcome back to linear classification. In this lecture, we'll be focusing on the discriminant model as contrasted against the discriminant function that we discussed in the last lecture. If you remember, discriminative functions are functions that map data points directly to a class with no need to try to calculate probabilities. Discriminative models, they up the ante just a little bit in terms of complexity by modeling the posterior of the data points so that we can better classify new data points and also have probabilities to help us classify data points that are not linearly separable. But remember that we're modeling the posterior and not the prior. We're going to jump right in to the discriminative models with logistic regression. Now, I'm going to make a special point right now, so listen carefully. Logistic regression is a classification method, not a regression method. You remember the difference between classification and regression, right? So why is it called logistic regression? Well, if we look at the binary case here below, we see a familiar form of the posterior, namely X transpose W plus beta. That's the form that we remember from linear regression. The difference here, however, is that we have the function sigma encapsulating everything. Here, sigma is the sigmoid function, also known as the logistic function. This function forces the values of X transpose W plus beta plus B to stay in the interval from 0 to 1. Now, you may be asking yourself, why are we using the sigmoid function? There's got to be a good reason, right? Well, historically, people's reason for using the sigmoid has changed over time. In early work, it was justified because it was a solution to a particular differential equation. This was when continuous time formulations tended to dominate. When discrete time formulations dominated, it was justified more heuristically as a monotonic squashing function. Essentially, the reason it is justified today is because it is a natural representation for the posterior probability in a binary classification problem. If you'd like to know more about the history and the derivation, check out the paper by Michael Jordan that I have mentioned below. We will also cover this to a minor extent in the next video in this series. That is, when we talk about generative models. Here I've included the definition of the equation as well as its first derivative. I hope you notice that this is a very nice form for the derivative. It's also useful in the next slide. So we know from our discussions about linear regression that we need to learn the parameters of the model from the data. So we follow the same procedure as then, and we try to maximize the likelihood. Here, I've written out the form of the likelihood conditioned on W and on X. But remember, sometimes we leave out the X term for notational simplicity because we never condition on the input data. So we know that the likelihood is the product of the conditional likelihoods for each class. In this case, we have two classes, so we can write the likelihood as you see here. Now, I've written the class term a little different than in my previous notation, so it is a little bit more intuitive to read, I think. Here, Z equals 1 means that Z belongs to class C sub 1 or class 1. This new way of writing makes sense when you notice the exponentials of the two factors of this equation. Let's look at those two factors that exist in this two-class likelihood. As you can see, only one of these factors will be active at any given time because of the exponentials that are on each factor. For example, if Zn is equal to 0, then the first factor will take precedence. However, if it is equal to 1, that is, it belongs to class 1, then the second factor will take precedence. Now, since we need to maximize this likelihood to get the optimal value for our parameters, we use logarithms to change the product into a sum. You'll notice that the y sub n is the linear form that we saw before. It's also the form from linear regression, and it's made nonlinear by this sigmoid function. The form of this error function, after applying the logarithm, has a special name that you might have heard before. It's called the cross-entropy error function, or sometimes called the log loss. But I'll leave that to you to investigate. In linear regression, we were able to find a closed form solution because we had a set of linear equations. Now we have a set of nonlinear equations. That means that we don't have a closed form for the solution. Okay, so what do we do? Well, with a little bit of algebra, we can convert the derivative of the error function from the previous page, which happens to be this equation here. So what does this equation actually look like? Come on, does it remind you of anything? If you're thinking, Grady, that looks a lot like the gradient of the log likelihood function that we learned about in linear regression, then you're absolutely right, because it is. So how do we get to this derivation? Well, it's pretty straightforward if I give you a couple of hints. First, remember that we can manipulate a logarithm in this fashion. And second, remember that I gave you the derivative of the sigmoid function earlier. So try it out. See if you can go from the error function to this derivative formation. So just as we saw in linear regression, the maximum likelihood approach overfits the training data. In regression, we added a penalty term. Let's try to do the same thing here. I've written this error function as e tilde so that it doesn't get confused with the error function that we just discussed on the previous slides. This formulation should look very familiar to you, as it's the same formulation that we used for ridge regression. The difference here being the inclusion of the sigmoid nonlinearity. This equation is known as the soft 0-1 loss function. When beta goes to infinity, the equation becomes the 0-1 loss that we discussed in the last lecture. Lambda is used to control the complexity of the model, just as it did in linear regression. And unlike ridge regression, this equation is not convex. That means we're not guaranteed to find the optimal solution. Here's an example of logistic regression using maximum likelihood priors against soft loss. Logistic regression is heavily influenced by the outliers in this example. Intuitively, the cumulative mass of the data points is what logistic regression bases itself on. This means that severe outliers can have a large effect on the algorithm unless large amounts of data are used where there are few to zero outliers. The penalty term built into soft 0-1 helps to prevent this exactly like it did with ridge regression. So what other alternative options do we have for loss functions? Well, one very common one is called Hinge Loss. It gets its name because the function kind of looks like a door on a hinge. Intuitively, it kind of approximates the logistic regression error function. If you look at the chart on the left, hinge loss is represented by the blue line here, which you can see kind of looks like a door on a hinge. The red line is logistic regression. Again, this red line, though, is rescaled so that it does pass through this point 0, 1. But as you can also see here, this black line, that's the 0, 1 loss that we discussed in the last lecture. And the green line is the squared error. So why would we use this error function? Well, it has a few nice properties. Since it's non-continuous, it isn't differentiable on the entire length of the function, but it is locally differentiable, which is good enough for a lot of cases. You can also use a version of this function called squared hinge loss, where we square the output of the max function. This enables us to punish data points being in the wrong place with a quadratic instead of a linear punishment. But it is more standard to use normal hinge loss. The equation is semi-robust because of the linear error penalty. And lastly, we have a convex objective to optimize. Another nice thing about this function is that it has a built-in margin. A margin is a specified distance from the decision line where points can be penalized for entering. This helps to make a more robust solution as well as shrink the version space of the algorithms. The version space is just a fancy way of saying the space of all possible solutions to the problem. The one value you see in the equation can actually be replaced by a 0 or a 2 or 1.2, essentially any value g, where g is a constant. Now, you have to tune this parameter in order to get an optimal agreement between the size of the version space and getting a solution that is optimal. If you have too high of a margin, you may force the algorithm to decrease its lower bound to accommodate. When g is set to 0, it is sometimes called the central hinge loss. In case you run across it in any reading, I just wanted to mention it. Here's also a good point for me to talk about convexity and robustness. Here again, we have two items that oppose each other. 0, 1 is a very robust loss function because it assigns the same penalty to any misclassified points. Loss functions like squared loss assign an exponential loss function to misclassified points, and this causes them to be highly affected by points far away from the decision boundary. If we want functions that are more robust, they would look something like this. But the problem with this function is that it's no longer convex because of this. So we have a trade-off here. What you will probably find in the literature is that most people tend to preserve convexity rather than robustness so that they have an easier time optimizing. It's usually at this point in the lecture that I assume one of you watching thinks to themselves, well, that's just peachy if you only have 2 classes. But in the real world, we're going to have more than 2 classes, right? Right you are, my friend, right you are. In the multi-class case, we make Z a vector so that it takes a 1 if it belongs to that class and a 0 if it doesn't. This is often known as hot K encoding or hot 1 encoding. If we have 8 classes, this would be called hot 8 encoding. That also means that our vector W is no longer a vector, but rather a matrix W. If you remember back to our notation guide, matrices are demarcated by being uppercase and bold. In order to model the posterior of the multiclass logistic regression problem, we use a function called the Softmax Function. We'll talk more about this function in the next lecture. Essentially, we have a set of linear functions, similar to what we saw in one versus all classification from the last video. For each class, the function is normalized by the sum of all the other functions. This gives us a probabilistic way of viewing class membership. In order to derive the gradient of this function, we follow steps similar to what we saw in the binary case. And as should be expected, this gradient has a form that we've seen before. What form do you think that is? Well, it turns out that it has the same form as in the binary case of logistic regression, as well as what we saw in the sum of sum of square errors function. This is namely the error between our prediction and the label times our basis function. I'll leave you to discover that for yourself. So in classification, we've seen lots of algorithms that don't have the nice closed form solutions that we saw when we did regression with conjugate priors. So how do we solve these problems? Well, we need to use optimization methods. Methods you might have heard of are stochastic gradient descent, Newton-Raphson, BFGS, or others. The thing to remember with these algorithms is that if the algorithm is non-convex, you aren't guaranteed to find the optimal solution. Even if the algorithms are convex, problems in the optimization method or initialization of the optimization method could prevent you from getting the absolute maximum or minimum that you're searching for. Instead, you'll get something close if things work out nicely. I emphasize that these methods will find you a minimum or maximum because depending on the method and how the problem is formed, there could be an infinite number of solutions that give you the same answer. A great example of this is when you use the 0-1 loss or the hinge loss. There are an infinite number of lines that you could draw between points to get the same 0-1 loss. Now, as exciting and critical as optimization methods are to know, we don't have the time to cover them properly in this lecture. They will be covered, however, to a small extent during the neural network lectures. You are free, of course, to dig into them on your own. Any decent numerical analysis book should get you started on the right foot. I hope you learned something today about discriminant models and their use in classification. Up next, we'll be talking about generative models. Thanks for watching and have a great day.